So we finally made it to what I'm going to call 9 plus, the applications of differential equations. So we learned what differential equations are, and then we looked at separable equations, and we looked at linear differential equations. So now we're going to see applications for separable and linear. It turns out I've got two styles of applications for both of them that would have appeared at the end of 9.2 and the end of 9.3. I find it's really overwhelming to throw these applications into those sections. Much better to just give it a full day's attention on its own just to learn the new technique that we've already done, and then give it a full day to look at the applications. I just find that you kind of need that time for those solving techniques to sink in. Okay, anyway, here we go. So in this first video, I'm simply going to tell you what the 4 applications are, and then we're going to spend one video doing an example of each of the 4. So there'll be 5 videos here in 9 plus. It's a long section, but because we already have these solving techniques down, then there's maybe a lot of writing, but we're kind of just really practicing those techniques as we look at how they apply to things. So it's a nice review at the same time. And we're going to be doing particular solutions in every situation too. Okay, here we go. Enough talk. Here is what I've got. Here's the first application. It's about exponential growth, which also applies to the idea of continuously compounded interest, which maybe is something that you saw in an algebra class. Comes back again in calculus, kind of cool. So I've got the same differential equation here, although it's written a little bit differently depending on how we're thinking of it. If we're thinking of it as exponential growth, then the differential equation looks like dy over dt equals k times y. If we're thinking of it like it's compound interest, then we call it dA over dt equals r times a. So what's up with that? Well, kind of the y and the t and the k are like the general sort of variables that you go with, but if you're talking about it specifically as like an amount of money with interest, then we like a for amount and r for an interest rate.
Hello.
Oh, thank you.
There you go. You're welcome.
Thank you so much.
You're welcome.
Excuse me, I just had a package delivered here on my front porch. Okay, so an amount and an interest rate. All right, so where do these differential equations even come from? So it's the rate of change. It's probably easier to describe in this context. The rate of change of an amount is directly proportional to the amount itself. Okay, so think about money, right? Let's say your investment is growing at a certain interest rate, right? Well, if you don't have very much money in the account, then the amount is not going to be changing very quickly, right? If you've got $100 in an investment, and hey, you might be getting a killer interest rate on that $100, but it's only $100, so that the $100 is not going to be growing very quickly. Like maybe you make $1 per month or $5 per month, right? If you're really killing it, maybe you make $10 per month. Not very much. What if instead of $100 in your account, you have $100,000? Well, then that same interest rate, right, you might gain, $1,000 a month or $10,000 a month, right? I mean, it's really going to be growing quickly. Same percentage-wise, but the bigger the amount, the faster it grows is the idea. And same thing back here, So a lot of times exponential growth, we're talking about like population size and how fast a population grows. Well, if the original population is really big, then the rate of change in that population is going to be, the growth is going to be really fast, right? The K really acts the same way as the R, right? It's like a percentage. We call it K in general, but it's still going to work like an interest rate, like a percentage. Okay, so the rate of change in the amount, the derivative, is directly proportional. It's some constant times the original amount itself. Okay, so I spend a lot of time explaining this first example because it turns out, this first application, because it turns out the next two applications just build on this idea. So we're just kind of like tweak this idea. But this is really foundational. Okay, so how would you solve either one of these styles? Okay, these are going to be solved by the separable method that we saw in 9.2. Okay, so we can do the separable equations thing and integrate both sides. We'll save that for the next video, an example of this. Let's move on to the second type of application. Let me try and keep this on the screen if I can. I don't know if it's going to work. Oh, it does. Okay, cool. So this is called limited growth. So we start in the same way that we do the exponential growth, but now we say there's a limiting value. All right. So with exponential growth, things can just grow and grow and grow and grow and grow, bigger and bigger and bigger and bigger forever. That's kind of the idea with like an interest rate, right? The longer you leave your money in, the higher it goes, right? And in theory, you could leave your money compounding interest forever, and it will grow to infinity. Now, you'll never get to do anything with it. You'll never get to pull it out and actually spend it. But in theory, right, that would happen. Limited growth, a little bit different. Let me show you the graph. It's not just going to go up forever and ever. It's going to have, some initial value, okay, and then it's going to kind of do this. It's going to have some like maximum, something like that. So, maybe we call this value the M, right? That's the limiting value. It'll approach this, but it will never exceed. Okay. Truth is, you can actually have this is an upper limit. You can also have a lower limit, and I didn't really give myself enough space for this, but maybe you've got this lower limit M, and it shrinks down like that. Okay, I kind of went off the screen a little bit. This could occur as well. So maybe the exponential graph is coming down, but it's never going to go below that limiting value. Either situation uses the same differential equation. And you can tell all that happened was, instead of k times y, it's now k times m minus y, right? I mean, nothing, right? The only change was here. So what's up with that? How is that the differential equation? Well, think, hey, if y ever gets to m, then it's going to be zero change, right? If it ever gets to m itself, it's just going to sit there. Because if y is m, then you've got m minus m, you've got 0. The derivative will be 0. The rate of change is 0. It'll just sit there as a horizontal line. The idea is that m is getting closer, y is getting closer to m, and so the rate of change gets less and less. So it increases slower and slower. Okay, anyway, end of the day, you need to know the differential equation. That's the second application. We're going to solve that by separable as well. Okay, the third application, again, there's this similarity. This one's really cool. An annuity. So continuously compounded interest, obviously that's got a lot of applications. But annuities are taking it a step further, and they're really probably more realistic to what people do with their money, right? They don't just let their money sit in an account and gain interest forever, and they never touch it. They take money out, right? So an annuity means that you've got a certain amount of money in your account, and it's gaining interest, but you're also making withdrawals. So we're going to keep it simple. We're going to say you make withdrawals each year. you always withdraw the same amount every year. So your money is gaining interest, right? R times A is the interest that it earns. But then you subtract how much you withdraw each year. Okay, so now we've got a very different differential equation. It's actually no longer separable, it's linear. So what we're going to do, it's not in the correct form. If we subtract that R times A, then it's a linear differential equation, right? What was that? The original style we saw was y prime plus f of xy equals g of x. Well, you know, we've got minuses and stuff now, and we've got a instead of y, but that's the form. It's a linear differential equation. Okay, obviously we'll do one example of this a few videos from now. The last application that we will look at is equilibrium price. Now this one is significantly different than the other ones. This one's about supply and demand. The equilibrium price is defined as when supply equals demand. What price should you make your product so that you sell all of the units that you produce? So the amount that you supply, they all get purchased. That's exactly the demand. Well, that would be nice. There's really not a lot to say here. We'll have to see it in an example, but when we do, they're going to give us an equation for supply. They're going to give us an equation for demand. We're going to end up setting them equal to each other. Okay. The solution we call P of t. It's the price at time t. So we want to know what price should we set our product to make supply equal demand perfectly. And that price could change as time goes by, right? So as time goes by, our supply and demand change, so we have to change the price to keep these equal. Pretty cool. So we're going to solve this in the linear style as well. Again, more details when we do that one later. Okay, so these are the four applications. I'm going to stop this video here. We're going to do each on their own. That's coming up in the next video.